Good evening, or good morning, or good afternoon, everyone. It's almost time to start our session. So welcome to session 5 of SoCC 2020, session 5 called Centralized Computation. And this session has 4 amazing papers. I'm going to read their titles first. The first one is GOSIG, a scalable and high-performance Byzantine consensus system for consortium blockchains on wide area networks. Okay. The second one is SHREC, bandwidth efficient transaction relay in high throughput blockchain systems. The third one is making edge computing resilient. And the fourth one, specializing the network for scatter-gather workloads. So we have these 4 papers today. The session is going to last for 1 hour. So for each work, we are going to have 15 minutes. The first 4 minutes are reserved for the panelists, for the author to present their paper in a lightning talk. After that, we have around 10 minutes or 11 minutes for discussion, for answering questions. So I also want to encourage people to ask questions. So please use the Q&A feature of Zoom to ask questions. Okay, so let's start with the first paper, GOSIG, a scalable and high-performance Byzantine consensus system for consortium blockchains on wide area network. And today we have Peilun Lee here to present and then to answer the questions. Peilun is a PhD student at the Institute for Interdisciplinary Information Sciences of Tsinghua University, working under the supervision of Professor Wei Shu. Okay, I'm going to share his presentation. Just allow me 1 minute to see where. Okay, so I'm going to share his slides. Okay, go see. So. Okay. So Peilun, you can start the presentation and let me know when I should move to the next slide.
Okay, thanks. Hello, everyone. I'm Peilun Li from Tsinghua University. Our work GOSIG wants to build a scalable and high-performance consortium blockchain on the wide area network. We think safety has the highest priority and no double spending should be allowed in any environment. So we want to keep safety property even in an asynchronous network. Then the fact is that in most time, there are no attackers. So we want to have an optimal performance in a normal case when there is no failure present. For the wide area network environment, it is not difficult for the attacker to launch DDoS attacks, and they can adaptively choose a victim to partition in this way. Many previous work like PBFT will suffer a liveness loss when the leader is under such attack. So we specifically designed a protocol to avoid losing liveness under adaptive attacks. Could you help to show next slide?
Okay.
Thanks. Here we summarize the key designs in GOSIG. The protocol proceeds in synchronized fixed-length rounds. Each round has 2 stages. The first stage is for the potential leaders to propose. It relies on secret random leader election to defend against adaptive attacks. A node secretly knows whether it is a potential leader and can generate a proof for this. If it is a potential leader, it will propose a block along with the proof. The second stage has an optimal 2-phase voting to commit one proposal in stage 1. If a round fails, it relies on later rounds to make progress. Then to get a better Scalability, we use aggregated signature gossip to reduce the signature size along the gossip process. It allows two arbitrary multi-signatures to be further aggregated asynchronously. Combining it with gossip ensure that no server will become a bottleneck during signature connection. The bandwidth reduction is evenly distributed among all participants. And at the implementation level, we pipeline adjacent rounds and stages and divide a block into several parts for better pipelining. By overlapping the propagation of all kinds of messages, we can fully utilize the limited network bandwidth to achieve an optimal throughput. Finally, we evaluate the system performance on the wide area network. On a testbed consisting of 280 nodes deployed on AWS with 14 regions across 5 continents, we can reach 50,000 transactions per second throughput with 16-second latency. Then we scale the system to 5,000 nodes with emulated wide area network environment, where the bandwidth is limited to 20 megabits per second, and we use latency data from 20 big cities across the world. In this setting, we can still achieve 30,000 transactions per second throughput with 24-second latency. Okay, that's all. Welcome to ask the questions.
Okay, thank you. I'm going to stop the sharing. Okay, question. It seems that there are no questions at the moment. So please, everybody, please ask some questions. Okay, since there are no questions here in Zoom, and also I see there are no questions in the app also, I'm going to ask you a question. So I see that on 218 nodes, your performance is 15,000 transactions per second. What is the peak throughput of your system? Like, for example, I don't know, if you use 100 nodes, are you achieving a higher throughput, or is it about the same?
Normally, it will, with more nodes, it will decrease the throughput because the blockchain workload is executed on all participants. And giving more nodes, it will, even given the same block size, it takes longer time for the block to propagate to all the participants. So it gives us longer latency, and given the same number of transactions, the longer latency means lower throughput.
Okay, yeah, but I mean, if you decrease the number of nodes, so let's say you have, because you say on 280, but what about, let's say, if you have half, 140 nodes, is it higher?
It will, it will increase throughput a bit, but it does not have much difference because given this kind of throughput, it has almost saturated the bandwidth of a single node. So, and in our experiment, we see in 280 nodes, 80% of bandwidth have been consumed by just propagating the transactions. So even you have much less nodes, the best you can do is to reach 100% usage of the bandwidth, and you increase the throughput by like 10% or 20%.
Okay, so by bandwidth, you mean the bandwidth of the network, right? Yeah. I see. Okay. Yeah, I think we still don't have questions here. Let me see. Yeah, no questions. What can you say about the the interblock the timing, the R that you showed in the plots. How much is it in your testing, in your evaluation? Like how much does it take for one round to complete?
Okay, in our 28 test bed, we use 10-second round, and the two stages are evenly divided. But actually,
okay.
the propagation of block only takes like 3 or 4 seconds, and the propagation of two-phase voting is also 2 or 3 seconds. But we just need set it a little longer to tolerate some workload burst or something like that.
Okay. Since there are no other questions, I think I am just going to go to the next presentation. And
okay.
But I mean, if there are other questions, you can use the app to ask the authors. Yeah, thank you, Pelon. It is a great work. Okay, now the second one. Second paper today is SHREC, bandwidth efficient transaction relay in high throughput blockchain systems. And it is supposed to be presented by Chang Xing, but let me see if I can find him. Previously, I didn't find him. Ah, yeah, okay. I will just promote him now. Sorry for that. Hi, Chengxing. Can you hear me?
I hear you. Let me check. Open my video. Okay. Hi.
Okay.
Hi to me.
Okay. Let me introduce you first. So, Chengxing Li is a fourth-year PhD student at Tsinghua University, and he's also a researcher in the Conflux project. His research focuses on improving the performance of blockchain systems. I'm going to share your slides, and then just a second, and then you can start the presentation, and you have to let me know when to go to the next slide.
Okay.
Okay. Okay.
Okay. Can I start now?
Yeah.
Okay. Oh, thanks to me for introduction. So hello everyone. Now I will introduce our work, the SHREC, a transaction dissemination protocol in a high throughput blockchain system. So nowadays there are many research are working on increase the performance of the blockchain system. And in the previous, the consensus protocol is the bottleneck of the blockchain system. And the recent work can increase the throughput of the consensus protocol significantly. And now the transaction dissemination becomes the next bottleneck. In a blockchain system, when a node receives a transaction from a client, it is required to broadcast this transaction to all the other nodes in this blockchain system. So, given a limited network bandwidth, how to support the transaction dissemination in a high throughput blockchain system? So in the Bitcoin design, when a sender receives the transaction, it will encode this transaction into a transaction ID and send this transaction ID to the other peers. And when a receiver receives the transaction ID, it will check whether one of the received transactions has the same ID. If not, it will request the sender for this transaction. This transaction ID is a 32-byte hash value of the transaction. Currently in Bitcoin, about 30% to 50% network usage are used for announcing this transaction ID, and we want to reduce this announcement. But if we use a shorter transaction ID, for two different transactions, they will have a same transaction ID with a high probability. And in this case, the receiver will only request one of them. And this design is also vulnerable under some hash collision attack. In Shrek, we have a hybrid encoding scheme. In Shrek, each node will share a different nonces with different pairs. And when computing the transaction ID, it consists of the two parts. One part is 3 fixed bytes from the last 3 bytes of the transaction hash value. And a random byte is computed from the hash value and the nonce. So for the same transaction, different nodes will send the transaction ID with different random bytes. This random byte provides the receiver additional opportunities to request this transaction. Okay, now we can move to the next page. Thanks to me. So, and we also need to defend the hash collision attack. In a hash collision attack, the attacker may send many transactions with the same fixed bytes. And when another node sends another transaction with the same fixed bytes, the random byte in the transaction ID will collide with the malicious transactions with a high probability. And now the receiver may not request this new transaction. In order to prevent this attack, Shrek says that if there are more than 9 transactions with the same fixed bytes, the receiver will request 32-byte transaction hash for the following transaction ID with the same fixed bytes, and this can resolve this problem. We evaluate our protocol in the Conflux project, and we also implement the Bitcoin flood, the SIP hash in the same code base. The network bandwidth is limited to 10 megabps, and we can see that the Bitcoin flood and the SIP hash is bounded by the network bandwidth, and Shrek can achieve 6 times of the throughput compared to Bitcoin flood. We also breaks down the bandwidth usage under a 500 TPS workload, and we can see that the Shrek can reduce the announcement of the transaction short ID significantly. So that's all for my lightning talk. Thank you, thank you very much, everyone, and welcome for any questions. Yeah.
Okay, thank you. Let's see if we have questions. Again, there are no questions here, but maybe you can tell us more about the Conflux project, like what are you doing in this research? Is it a research project or an industrial project?
Okay, so Conflux is a blockchain project, and it is a public chain. And now we have launched the mainnet of this project, and I am a researcher in this project. And my research mainly focuses on how to design a high throughput blockchain consensus protocol, how to reduce the confirmation time of the consensus protocol, and how to provide a rigorous security analysis for our design. And then my research moved on to some other topics, such like how to design a highly efficient transaction dissemination protocol for our blockchain system. And now we can see that since the transaction dissemination performance is resolved, and my research is moved on to increase the performance of the transaction execution. Yeah.
Okay, sounds interesting. Okay. Since there are no other questions, I'm going to ask you one more question here. So, okay. For example, you mentioned here that if there are more than 9 transactions with the same fixed bytes, the receiver will request for the full hash, 32 byte. But what is the probability to have such kind of transactions?
What?
Well, like in your experiment, what is the probability to have transactions with, to have more than 9 transactions with the same fixed byte?
Okay, so if there is no if there is no such an attacker, so it will happen with a really small probability. And we analyze this probability maybe 10 power to -9, or maybe lower. So we can say that it can never happen in absence of an attacker.
Okay.
And yeah, but if there is an attacker, this can indeed happen. That, yeah, and it depends on the behavior of the attacker, because the attacker can generate a lot of transactions with the same big bytes and broadcast it in the network, and you will see that, and this policy will be triggered. Yeah.
Okay. But I'm curious, like, do this kind of attacks happen in like Bitcoin? Did they ever happen?
Because Bitcoin sends a full hash, and you
okay.
cannot generate another transaction with the same full hash. So Bitcoin does have such problem, because Bitcoin doesn't need to consider the performance. Its consensus protocol has a really low throughput. So it can send the full hash and flooding this full hash to all the nodes. Yeah, and it is not efficient, but it is safe.
Okay, I see. Okay, let me check again to see if we have questions. I suppose it's late for everybody, and oh, it seems that we have. Okay, that's great. So there is a question here from Rojit Panda. Can you compare the hash reduction technique with techniques such as Falcon?
So I'm sorry, I'm not very familiar with that. So what is Falcon?
Yeah, I'm also not familiar. So maybe I don't know. Orojit can maybe give some details. Meanwhile, he also asked another question: how does topology compare to importance of improved hashing?
So my questions are basically related. So a lot of the existing work on improving dissemination has been on changing the network structure to enable fast dissemination. The idea being that, with both Bitcoin and with Ethereum, the fact that if you have large nodes that connect many, then dissemination is faster in terms of just the amount of hops that it takes, and the fact that you can potentially improve your network capacity. Here you're focused on hashing. So I wonder, what is the trade-off between these two? Like, this seems like a very different approach than what, for example, the Cornell people have been doing to get fast networks. So Lightning is the other version of this. Like, how does Lightning and this compare?
Okay. Okay, thanks for your question. So I think this is two different aim, because when we change the network topology, and our aim is to reduce the latency, to reduce the transaction latency or the block latency in dissemination of the transaction. And so Shrek, the aim of the Shrek is not reduce the latency, but increase the throughput. So we mainly focus on how to encoding this short ID, maybe use the hybrid hashing and some such scheme to reduce the announcement and utilize the network bandwidth effectively. So I don't think Shrek is a design for reducing the network latency, because when you consider the network latency, as you see, maybe the network topology is much important than the hashing mechanism. And so our let me check. So so in our paper, so Shrek also have some discussions for the latencies, but it is only discussing the latencies in the different parameters. Shrek have a parameter is that when a node receives a transaction, how many peers should you forward this transaction to? And our results show that if you have a low fan out, means that if you only forward the transaction to only 4 peers, and the throughput will be increased significantly, and it will achieve the similar network bandwidth latency. And so I can see that maybe maybe Shrek have the similar network latency with some similar works, maybe Bitcoin or some other works. Yeah, but it can achieve the higher throughput. Yeah, maybe it is another contribution. It is another contribution with the network latency. Yeah.
Thanks. That makes sense.
Yeah. Thank you. Thanks for your question.
Okay, thank you for answering. Let me see. Okay, no other questions here. So, yeah, if we don't have any other questions, we will move on to the next paper. So, yeah, thank you very much, Jiangxing, for answering the question and presenting your work.
Okay. Thanks to me.
Okay. So now the next work, it's about edge computing, making edge computing resilient. And we have today Aisha Mustaq to present and answer questions. Aisha is a 5th-year PhD student at UC Berkeley, working with Scott Schenker and Sylvia Ratnasamy at the Nessis lab. Aisha's main research interests include networks and distributed systems, with her current research focusing on designing consistent and fault-tolerant edge computing systems. Okay. I'm going to share the presentation. Okay. And let me know when to go to the next slide.
Thank you for the introduction to me. Hi everyone, I'm Aisha. And today I'm excited to talk about Cessna, which is a framework that provides resiliency for edge computing applications. So maybe we can move on to the next slide. So edge computing is becoming increasingly popular, and there are many applications that benefit from having storage and compute resources at the edge. Amongst these applications that are benefiting from using the edge, many of them are also session-based and stateful. So what I mean by session-based is that these applications establish a session between the client and server through the edge. And what I mean by stateful is that these applications keep state at the edge to provide either correctness for the application or to enhance performance of the application. And the important thing to note here is when you establish this session through the edge, the session's fate is now tied with the edge. And while the session's reliance on client and server was inherent, this addition of edge, sharing the fate with the session, presents a problem. And the problem is that now if the edge fails, our session can now fail. And recovering from these session failures is non-trivial when your edges are stateful. So if this edge fails and we recover through another edge, we could end up in an inconsistent state, or it can take really long to recover from edge failure while you're reconstructing the state. And there is a lot of literature on fault tolerance in distributed systems, and this literature basically relies on either replication or message replay to provide fault tolerance. However, these solutions do not fit well in the case of edge fault tolerance. And that's because most of the edges are resource limited. And this could be because there are many edges, and it's not feasible for us to provide adequate compute and power redundancy for all of them. And so we cannot use local replication as our solution here. Additionally, their performance requirements on these applications. So this limits the use of far-side replication or locking. So given these limitations, how do we design fault tolerance for edges? Can we move on to the next slide? So for Cessna, we choose to use a record and replay mechanism to provide fault tolerance. And what we do is we replicate the state at the client and the server in addition to the edge. And this allows us to limit the resource and performance overheads that are incurred by the application, and allows us to, by storing state at the client and server, allows us to restore freight sharing between the client and the server. So to go into a bit more detail, what we do is we have the client and server log their outgoing messages, and then we have the edge record the interleaving ordering of these messages in which they are processed. And then this edge provides the information that it is recording about the state to the client and the server. And so now the client and server have all the information they need so they can restore this session through a different edge. So upon failure, what the client and server do is they provide this information that they've been keeping to this new edge. And so this new edge retrieves the logs from both client and server and then replays them. And additionally, we rely on checkpointing to improve the efficiency of the recovery mechanism. For more details, I would encourage everyone to read Cessna's paper or look at the full presentation and also for the results. And with this, I'm happy to take any questions regarding Cessna.
Okay, thank you. Okay, let's see if we have questions here. Yeah, we still don't have questions. Okay, so let me see. So you are saying that basically now you are replicating the state at the edge and the server. So are you replicating at both at the client and at the server, or just?
So yes, we're replicating the state at both the client and the server. Okay.
But what are the performance implications of doing this replication? So now, because now, I mean, what is the role of the edge here if you keep the state at the client and the server?
So what we're keeping at the client and server is not like the entire processing of the edge. We're just recording what the way these messages were processed, like the order in which these messages were processed. So these are just like message IDs, you could say. So you're not replicating the entire state machine at the client and the server. You're just replicating the information needed to restore the state at a different edge. So when the edge fails, what you do is you provide the messages you had sent and the ordering information. So the ordering information is basically to provide consistency. We want to provide output message consistency to the client and server, which is what we're saying is that any behavior of the edge, while like the edge is executing a state machine, the state machine produces behavior that is observable by the client and the server. Now you want that if this edge fails, I want to see consistent state. So what the client and server have seen before, I want the same thing to be seen after a failure and recovery. And so the only thing that you need is the information to restore up to that state, and you're just using the message ordering to restore that and replaying those messages by the client and the server. So you're not having the edge, the client and server do the work of the edge. You're just keeping the high level information.
Okay.
Does that answer your question?
Yeah, I understand now. But now I have another question. So you mentioned that these edge devices are limited in terms of resources. Maybe computational resources or storage resources. So my question here is also regarding the performance, right? So is it better to do this at the edge, or maybe it's better to do it in the cloud or at the server side?
What at the cloud?
I mean, you mentioned that the edge is basically like running a state machine, right? But the edge has limited resources. So isn't it like more efficient to run the state machine in the server, or like, yeah?
So yes, you have limited resources, but you still want to provide either performance benefits, like you want to do bandwidth offload, sorry, you want to save bandwidth going up to the server. And so for instance, in a video analytics application, what you do is you have video streams coming in from the client, and then you want to do some kind of analytics intermediately at the edge before sending it off to the server. So now you're reducing a lot of redundant information going to the server. So you need the edge to be in between. So you the edge is basically having edge in between the client and server is offering multiple benefits to the clients or to the application itself.
Okay, so
and that's why you have the edge in between.
Yeah, I suppose you have like a kind of like a tree structure, right? One server, then maybe multiple edges, and maybe even many more clients connected, something like that, I suppose.
So we're talking about a session-based application. So in this case, we only have one client and server session, and many of the applications, edge applications, do follow this pattern. So video analytics applications, or think about TLS termination, or that kind of like sits in between the one client and one server session.
Okay, but I mean, you can still have multiple clients connected to the same server, right?
Yes, you can definitely have multiple clients connect to the same server. It's just that they are treated as different sessions through the edge. Yeah,
of course. Yeah. Okay. We also have some questions here. One question from Shivaram Venkataraman. How would some hardware trends affect Cessna? For example, higher bandwidth links with the adoption of 5G, or more efficient compute nodes at the edge, I suppose. For example, NVIDIA Jetson TX2. So like, what are the hardware trends? How does the hardware trends affect Cessna?
We want to provide survivability. So even if there are more resources at the edge, we do provide optimizations that if there are more resources available at the edge, or the edges are more efficient, you can use local recovery, and that would speed up the performance a lot. But we also want to guarantee survivability. So in case like the entire edge still fails, we want to, and the client and server are still alive, we want to restore this session. And so if you have more resources at the edge, you can use them to improve the efficiency of Cessna and use the remote recovery as sort of a fallback mechanism.
Okay. Any other questions? Not yet.
I think there is one in the chat saying, what are the latency overheads?
Yes, what are the latency overheads? But I don't know what. Yeah, okay.
So for latency, so there are two kinds of overheads that Cessna could impose. There are bandwidth overheads, and that's on every message we do pen a short header to disseminate this information to the client and the server. That's around 2% for bandwidth overheads. And for latency overheads, like during message, like when you're appending these headers to outgoing messages, there's not a lot of overhead, like it's negligible, but during checkpointing, this overhead can be slightly larger. So it takes around like, let me see, around, so if you had like a huge amount of state, like 10 MB state, to checkpoint that, it would take 43 milliseconds, but that's like a really big number, which I'm using. You usually have much less overheads than that.
Okay, thank you. There is one more question here from Dmitry Ustyugov. Regarding the recovery time difference between Docker versus using specialized structure, is the difference attributed only to the memory footprint difference, or there are other overheads? As an idea, would it make sense to implement incremental differential checkpoints for Docker to capture only the dirty pages to cut the recovery time?
I think most of the overhead in Docker is coming from like the memory footprint, like they're taking in a lot of the information that is not really needed, and they don't have incremental checkpointing. So having like, so when you're talking about incremental checkpointing, you also want to make sure you're only storing state that is necessary for the application and not all the other structures that are surrounding it. And then, so it would make sense to have incremental checkpointing and just checkpoint only the state that is needed for the application.
Okay, thank you for answering the questions. Let me see, do we have one? No, we still have. We don't have another question. So, oh, I think we have some question now. Or yeah, how is from Wan Zhang? How would you compare the setting of Chestnut to serverless computing in the cloud? For example, AWS Lambda.
So most of the cloud application, the serverless implementations are stateless. So they require that you store state in services like S3 or something like that to store state, whereas we're talking about having stateful applications that store state for these applications. This like with the most of them are stateless or have soft state, but like with the exception of Azure Durable Functions. So Azure Durable Functions do allow storing state at the applications using like these activities. And however, for Azure Durable Functions, you do need restructuring of the application and to use that, and we require minimal changes.
Okay, thank you. Okay. So thank you very much, Aisha. I think we don't have any other questions, and we're going to move on. Thank you very much.
Thank you.
The next work is specializing the network for scatter-gather workloads, and we have here Catalina Alvarez and also Zhanghao He to present the paper and to answer the questions. So let me first share the screen for the presentation. It's also just a second. It's here. Okay. But before that, let me introduce the presenters. So Catalina Alvarez is a PhD candidate at the Systems Group at ETH Zurich, working under the supervision of Professor Ankit Singla. Her research currently focuses on understanding how different network applications deal with uncertain quality of services, looking for possible improvements across the entire network stack. Then Zhenhao He is a PhD candidate at the Systems Group, ETH Zurich, under the supervision of Professor Gustavo Alonso. His research focuses on designing customized hardware accelerators for computationally intensive tasks, such as machine learning. He is also interested in exploring in-network processing with customized hardware. I am going to share the PDF, and are you guys going to present alternatively or only one of?
No,
okay,
thank you for the introduction. I'll be presenting.
Okay, thank you.
Well, hello everyone. My name is Catalina Alvarez, and my talk today will be about speeding up communications for scatter-gather communications. The name scatter-gather refers to workloads in which one node, we call that the controller, communicates with hundreds or even thousands of other nodes, the workers, to run a distributed task. This kind of pattern appears commonly in applications and frameworks running data centers, such as data analytics, search engines, and distributed graph processing, among many others. In this kind of applications, it's common that the computation in each worker is designed to be small, making the communication the biggest contributor to completion time. Unfortunately, network stacks are not optimized for this kind of pattern, with many short flows across many different endpoints, incurring high per packet and per connection overheads. Please, next slide. Thank you. Considering the previous points and the inefficiencies that scatter-gather present, we claim that an efficient scatter-gather as a service implementation should be made available by cloud providers. This way, users can just invoke it like any other service today, integrating it with both existing and new applications. In particular, in our work, we explore how a provider could present a highly performant scatter-gather primitive by specializing hardware for it. For our design, simplicity is key to make sure that all parts involved have an incentive to adopt our solution. On the infrastructure side, we propose offloading both the scatter and gather phases to a smart NIC. This idea on purpose aligns with current developments in data centers. On the client side, our scatter-gather primitive will be made available to invoke through a simple API, which abstracts all the details of the communication from the user. In our paper, we show that offloading TCP/IP to hardware improves the scatter phase, but not the gather, due to the presence of a problem known as throughput collapse. We present a simple solution to this problem suitable to implementation with a limited hardware footprint, and show that our solution solves collapse and improves completion time 5 to 16 times across different scenarios, even with variable and unpredictable background traffic. Thank you very much for your attention, and I would be glad to take your questions.
Okay, thank you, Catalina. Let's see if we have questions here. I think we have one question from Vivian Fang. Are there other applications, workloads, or workload patterns that could benefit similarly from offloading to smart NICs?
Oh, that's a good question. Different kind of workloads have different requirements. And yes, there are others. In particular, we could use a scatter-gather, for example, for other applications that in general do not look like they have a scatter-gather pattern, but they have either one of the phases. For example, in MapReduce, there's a scatter phase in the middle. So we could use a similar technique to improve that kind of application as well.
Okay. There is also another question from Orojit Panda. As I understand it, your implementation is on a bump in the wire FPGA per server. Can you compare this implementation versus one in the network, for example, in a programmable switch?
Oh, thank you for the question. We in purpose decided to minimize the intervention on the data center to make this our solution easily deployable. So we didn't compare against something on the network, but we compared against solutions that reside just on the endpoints. But of course, there are solutions to similar problems, or actually the same problem as ours, inside the network. For example, NDP is such an example.
Okay, and as a second question, also from Orojit Panda, can you comment on how this primitive works in multi-tenant environments?
Oh, good question. Thank you very much. The whole idea of our implementation is that we as providers present an API to the users that can be called as any other service today, meaning that in our case, we implement everything on an FPGA, and every time a user wants to access it, we will instance our kernel on a relevant FPGA. The idea is that this can actually work in a multi-tenant environment. That's why we decided to minimize the intervention on both endpoints and just offload everything to a single SmartNIC.
Okay, thank you for answering. Yet another question here from Shivaram Venkataraman. Does your work benefit from using in-network IP multicast? Would that help scatter gather?
Thank you for your question, but I'm not sure what you are pointing at here. Could you clarify, please?
Just a second. I think also Orojit would like to ask the question live. Let me see. I will try to unmute. So before going to the question that I just asked, I will let Orojit to ask you for the previous question.
Yes.
Wait, you answered my question. I didn't have another one. You probably want to talk to Shivram.
Oh, because I saw that you said you want to ask online. So, but I suppose
no, I don't think I did actually.
Oh, okay.
No, so I'm sorry. I marked the question as having been answered live. Sorry for the confusion.
Okay, no problem. Yeah, thanks. Okay. So yeah, if Shivaram, do you have any other details for your question?
I think Chevron posted a follow-up to his thing where he asked, does the work benefit from IP multicast or other in-network primitives? Like basically, are there common fabric primitives that you could use and use to help with some of this?
Okay, now I understand what he means. Well, the biggest problem with the scatter-gather and similar pattern is that at a transport layer level, this is a problematic pattern because of the throughput collapse I mentioned during the talk. So one needs to be particularly careful about the timing of both the request and responses to avoid overloading switches inside the network, because a scatter-gather is defined by how synchronized workloads tend to be. In general, when we run a distributed task, we divide everything in basically equal chunks. So the workers tend to finish mostly at the same time, maybe with some staggering, and that generates synchronization in the responses that can overload network switches. So even if IP multicast can help us to mark a packet to deliver to multiple machines, that only solves the scatter part, because we would need still to solve the problem on the gather phase. And besides, one important part of the scatter-gather primitive is that sometimes we want to send useful information to the workers so that they can run their own task. So even if we mark packets to reach different machines, that doesn't help us much, because workers could receive slightly different variations of the same packet or the same query, let's just say. Does this answer the question?
So I just promoted Shivaram to panelist, so maybe he can tell us if this answers the question.
He's on Hoover. He cannot actually respond.
Oh, I see. Okay.
But he said it does answer his question.
Okay.
Okay.
Thank you for the question.
Okay, let's see. I think we have another. No, it's just a follow-up. Okay. Okay, I also have a question. Can this primitive be integrated with MPI?
MPI, yes. Yes, that's a good question. We actually targeted TCP/IP specifically. So there, depending on how MPI is implemented, we could or could not. Shenhao, maybe you have something else to add?
Yes, actually, I think this is a very good question. So from my understanding, the answer is definitely yes. And actually, from my side, I'm currently working on something related to this. And I know that there are in the industry and there are some other research group, they are also trying to either offload these MPI primitives into an FPGA, or they want to make it easier for the FPGA developer to write MPI-like applications. So yes, this is I think this is a very good idea.
Okay, yeah. Thank you. We don't have any other questions, and let me see. If there are no other questions, I think we are going to end a bit earlier, like 3 minutes earlier today. Thank you everybody for attending this session on decentralized computing. We had four interesting papers, very interesting papers today. So I encourage you to read the papers and to watch the full video presentations. And thank you for attending the session, and have a great